away. All right. So can you guys see my screen now?
Yes, sir. Yes, sir.
All right. So what we'll do is I'll just go over, okay, from the slides, but I will not read all of them one by one. So basically, I'll just give you the thought of that slide, and then we'll move on to the next one as soon as possible. Okay, since we don't have that much time anymore, actually. So we only I'm not sure if the midterm exam will start exactly May 24, but I think it's May 25, 26, and 27. So if I'm correct, so we still have two meetings left. Okay, and then we still have four modules that we need to discuss. So that is why we have to finish the module 3 and 4 right now, and then for this coming Thursday, we're going to finish the module 5, or if we can finish the module 6, then better. So you guys can have one more meeting left for you to to review or to finish all of the activities that I gave to you. All right. Well, anyway, so without a further delay, let's now start with the module 3, Kirchhoffs Law. All right. So, why do we have Kirchhoff's law from the very start? Well, basically, series and parallel formulas are not actually enough to solve some complicated circuits. Like, for example, this one, the bridge resistor circuit or the P networks circuit. Okay. So, those are the kind of circuit that we cannot just simply use Ohm's law alone to find the voltages and currents. Okay. So, that is why we have Kirchhoff's circuit law. Okay. So, who invented or found out this rule? It was developed by Mr. Gustav Kirchhoff. Okay, so again, same idea. Whatever, whoever is that person who was able to develop or founded or created that rule, then his last name will carry it out as the name of that uh, law or of that idea. Okay. So basically, this one came from the rule or law conservation of current and energy within electrical circuits. Okay, so he believes that. Let me just give you a short idea. So if we have a source of energy in here, okay, and then if we have a circuit, so it's a closed path circuit. So every time that it will pass through, let's say, a certain load or a resistor, it will leave a voltage drop. Okay, and he also believes that once you started in here, all of those, let's say, all of those energy will be distributed equally. Okay, to this one, to this one, and to this one. Okay, and then as soon as it goes back to this original source, it is now zero. Okay, so meaning he has already distributed everything onto the load or to the resistors. All right, so uh, his main point is it cannot be that there is a voltage drop in here if there is no source. Okay, so there should be always a source wherein it came from this very very start. Okay. Well, anyway, so in here you've come up with two rules. We have the Kirchhoff's circuit laws. I mean the Kirchhoff's current law and then the Kirchhoff's voltage law. Okay, so KCL is for the current and then KVL is for the voltage. All right. So let's talk about first the first law or the KCL. So in here, Kirchhoff's current law or KCL states that the total current or change entering a junction or node is exactly equal to the charge leaving the node as it has no other place to go except to leave as no charge is lost within the node. Okay, so basically the same with the voltage a while ago. So once it distributed, the voltages in here, okay, so of course it will go back to its original source. So the same with the current. Okay, so as we all know, voltage is proportional to current. Okay, so same idea with that. So if there is a current that is flowing in here, so of course, whatever is the current that is flowing from the very start, let's say 1 amp, okay, as it leaves, it's still 1 amp, okay. So it will not change, all right? So in other words, the algebraic sum of all the currents entering and leaving a node must be equal to 0. Okay, so we could use this formula as the foundation, or as the very basic formula for the KCL. I exiting plus I entering is equal to 0. Okay, so everything that will go in here, and then everything, okay, from the load resistors, how many, even though it's 1,000 of resistors, as time that it goes back to its original source, it is now equal to 0. All right. So this idea by Kirchhoff is commonly known as the conservation of charge. Okay. So if you guys are going to take a look on this example right here, okay. So if we have a current going in, we also have a current going out. Okay. So in here, the formula that we have used, if it's going in, okay, if it's entering, the sign of this one is positive. Okay, I think that is the only thing that you need to remember when it comes to entering. Okay, but when it comes to leaving, let's say it enters this node right here, and then of course it will leave, let's say, to this point, okay, which is again another current. Say this is your I1, and then this is your I2. Okay, so I1 is equal to I2. Okay, or I1 minus I2. Okay, so we have entering, we have positive, and then we have leaving, which is negative. Okay, so if you're going to use this formula, we have to equate this 1 to 0. Okay, so in here, I've just simply transpose or transferred the negative on the other side. That is why we have I1 is equal to I2. Okay, so if you guys are going to take a look at this one, so we have the single node right here, and then some currents are going in, and then some currents are going out. So for the blue one, I1 and I2 and I3 is going in, so that is why we have positive. Okay, and then for the I5 and I4, so we have currents leaving out. So in here we have negative I4 and then negative I5. Okay, so if it's leaving, you have a negative sign. All right, so are we clear with this one? Hello, hello. Were you guys able to follow the first law? Okay, we are already talking about the first law, the KCL. Okay, if it's going in, positive. If it's going out, negative. So those are the only two things that you need to remember. Okay, so super, super easy. Anyway, so we have more explanations right here. So positive for the going in, and then for the leaving currents is negative. And then here's the final equation, which is the same with this one. Okay, and then let's talk about node. So the term node in electrical circuit generally refers to a connection or junction of two or more currents carrying paths or elements, such as cables and components. Also for current to flow either in or out of a node or closed circuit path mass exists. So we can use KCL or Kirchhoff's current law when analyzing parallel circuit. So in here, you can say that junction is equal to node, or node is equal to junction. Okay, so let me just get this one. Okay, so actually a node is very, very obvious. Okay, so we could say that, this is a junction that is, going to R1. So if we have another one right here, this is still a node, okay, wherein it connects to another components. Okay, so this is another junction wherein there is another connection in here, another junction wherein there is again a connection in here. So basically, you cannot just simply say that this is a junction, okay, unless there is a, another path that will go to another path. Okay, so this is one path, but you cannot say that this is another node since there is no another path that will lead to another path or row. So if there is another path in here, let's say another resistor, so this is now considered as a node. Okay, wherein of course this one is also now a node. Okay, so yeah, that's basically the main explanation when it comes to node. When we say node, a junction. Okay, so if you know the meaning of a junction, then you already know the meaning of a node. Okay, so are we clear so far regarding with nodes? So those are nodes. So we have 1, 2, 3, 4, so 8 nodes. Hello, clear for the node? Okay, that's good. How about the others? If you guys are confused, so please let me know. Okay, so that's it for the node. And then we have now here the second law, which is a KVL. Okay, so KVL is, states that in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop. Okay, which is also equal to 0. So again, just like what I mentioned a while ago. Oops. So if we have a source in here, okay, and then it passed through, let's say, a certain resistors, let's say 2 only, okay. So of course, it will leave a voltage drop in here, and then again, it will leave a voltage drop in here. So as it goes back to the original source, it is now equal to 0. Okay. And also at the same time, if you're going to add the voltage drop of this resistor, and then the voltage drop of this resistor is equal to this main source of voltage, or the value of this voltage source. Okay. So that is why in here, where is that one? So in other words, the algebraic sum of all the voltage within the loop must be equal to 0. So this idea by Kirchhoff is known as the conservation of energy. Okay, so in here we have VA plus VBC plus VCD plus VDA. Okay, and if we have a voltage source in here, that is equal to that voltage source. Anyway, so we'll talk about more KVL. So in here, starting at any point in the loop, continue in the same direction, noting the direction of all the voltage drops, either positive or negative, and returning back to the same starting point. So it is important to maintain the same direction either clockwise or anti-clockwise, or the final voltage sum will not be equal to 0. So we can use Kirchhoff's voltage law when analyzing series circuits. So in here, it is just saying that, if you have this kind of polarity, then you must stick with that polarity. Okay, you cannot have two polarities at the same time. So if you have clockwise, just stick with clockwise. If you have counterclockwise or anti-clockwise, then just stick with that. So in my case, I always go clockwise. Okay. Well, sometimes I use counterclockwise, but there's an 80% chance that I'm confused when I'm using counterclockwise. So mostly I usually go with the clockwise. Okay, like right here, from left to right. All right. And also when analyzing either DC circuits or AC circuits using KCL, a number of definitions, terminologies are used to describe the parts of circuit being analyzed, such as node, paths, branches, loops, and meshes. So these terms are used frequently in circuit analysis, so it is important to understand them. So we have already discussed what a node is, and then a path is just, this is a path, this is another path, another path, another path. So basically, the one that is between, okay, between the node, okay, that is the path, okay, another path, another path, and another path, another path. Okay, those are the path. And then for the branches, so we'll go over with the branches later, and then the loop and message. But for now, let's talk about the two types of flow of current. So the one that I use, okay, is mostly okay, conventional current, okay, or the clockwise method. So we also have the one that is being called the electron current, which is the anti-clockwise or the counterclockwise. But uh, I don't use this one, but it's up to you. They're the same. They're both the same. So you can come up with the same result. Okay. But in my case, I usually go with the conventional current. Okay. So from here, going here, and then going there. Okay. So conventional current. All right. So in here, just some common terminologies when it comes to solving a KCL or KVL. So circuit, you guys already know this one. So circuit is a closed loop conducting path in which an electrical current flows. And then path is a single line, okay, of connecting elements or sources. So just like what I mentioned a while ago, this is a path, another path, 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 path. Okay. And then for the node, so this is a node. So you guys already know this one. Okay, the one that is connecting, or it leads to another path, basically. Okay. And we have here a branch. So a branch is a single or group of components such as resistors or a source which are connected between two nodes. Okay. So if we have path in the between nodes, we also have the one that is so-called branch. Okay, let me just change the color. Oops. So maybe you guys are wondering why is the language of my PDF is something like this. Okay, because this is just a crack version. Okay, this is a Russian application, I guess. Okay, let me just get this one again, since the one that I copied is already messy. All right, so if we have a path, okay, between that node, we also have branch. Okay, this is one branch. Okay, this is another branch. Okay, but this one is not a branch. Okay, why? Because it doesn't have any component between it. Okay, so you can only call that it is a branch if if it's between a nodes and it has a component between that, okay, or inside of that. So like this one, it has the R1, this one has the current source, this one is another branch, and then another branch. Okay, so those are that we are calling a branch. Okay, let's go back in here. So again, it's a single or group of components such as resistors or a source which are connected between two nodes. Okay, so you can have multiple components. So let's say another component here, another component. So this is still a branch wherein we call this one now a group. Okay, so if it's just one component, that's one branch only or a single branch. All right. So are we clear so far regarding with branch?
Yes, sir.
All right. And we also have here loop and mesh. So right here, I will discuss the loop and mesh at the same time. So let's bring this one back. So let's define loop first. So loop is a simple closed path. Okay, that is the only thing that you can you can think about loop. Okay, as long as it's a closed path, that is already a loop. Okay, so in a circuit in which no circuit element or node is encountered more than once. And for the mesh, a mesh is a single closed loop series path that does not contain any other paths. Okay, so in here it's quite tricky at first, but all you need to remember is this terminology right here: single closed loop. Okay, so in here it's closed path, but in here it's single closed loop. Okay, so let me explain this one using this diagram right here. So if you guys are going to take a look at this one, we have a loop in here. Okay, so we can also have a loop in here if you want. It's also possible. And then we have another loop in here. Okay, and we can also have a loop outside it. Okay, from this point going back to its original position. Okay, so all in all, we have 1, 2, 3, 4 loops. Okay, so you could say that all mesh, okay, all mesh is also a loop, but a loop cannot be a mesh at the same time. Okay, so basically a loop is higher than a mesh. Okay, so it's below that loop. Why? Because we only have 3 loops in here. Okay, so if you guys are going to take a look, it's one single closed loop. Okay, so where are those meshes? So we have this first mesh. Okay, second mesh, and then the third mesh. But the last one in here, we cannot call this one as a mesh because this is not a single closed loop. So if you guys are going to take a look at this one, inside it, there is another loop. Okay, so if it's a mesh, so it should be, only one loop in it and then inside it. Okay, there should be no other loop inside of it. Okay, just like this one and this one and this one. But the outer one cannot be called a mesh because there is another loop inside of it. Okay, so it says also here that path does not contain any other paths, so that is why it's called a mesh. Okay, it only has one path, just like this. Okay, so I hope we're clear with that one. So were you guys able to follow? So all in all, we have 4 loops in here. Okay, and then we have 3 mesh. Okay, and at the same time, so mesh can be also called a loop. Okay, but to be specific, when you say mesh, it doesn't contain any path inside of it. Okay, so were you guys able to follow regarding with the term loop and then the term mesh?
Yes, sir.
So anyone who's confused? All right. Okay, so anyone before we proceed to the next slide? All right, so maybe none. Okay, I really hope so. All right, so moving on, we have here the sample circuit diagram of a branch. So like what I mentioned will go, so this is a branch, but this is not a branch because it doesn't contain any component between it. And then this is again another branch, and then another branch in here. All right, and then more explanation when it comes to a node, a branch, and then a loop. So in here we have a branch AB, BB, CD, BA, EA, AG, like those. Okay, but EB, so this one doesn't have any component between it, so this is not a branch. So it's just a short circuit. Okay, and then we have here a loop from A to A. Okay, and then inside of it, of course, we have 4 meshes. So one mesh, another mesh, and then another mesh right here. Okay, so note that components are said to be connected together in series if the same current values flows through all the components. So this is just a reminder. So if we have series, currents are equal between it or inside of it. But in parallel, okay, so you could say that it's parallel if they have the same voltage applied across them. Okay, so the one that is being equal in parallel is the voltage. Okay, series current. If it's a parallel, then voltage. All right. So this is a typical DC circuit. So again, more explanations when it comes to nodes and a branch and then a loop. Okay. So let's have an actual example regarding with the KCL. So find the current of flowing in the 40 ohm resistor R3. So in this case, I will use this one and I will copy and paste it right here. And I will get the solution and paste it beside it. And let's see if we can fit this solution color paint. All right. Well, anyway, so let's go over with the from here first before here. So we have the circuit right here. We have 10 volts, another voltage source right here, which is 20 volts, and then another another. So we have components right here, R1, R2, and R3, and then their values. So we have this current right here for the R1, and then another current right here for the R2, and then they will meet on this node coming up with another current which is I3. Okay, so in here, the one that I've used or we've used is the conventional current. Okay, so as you guys can see, we have uh, clockwise, but in here we can say that this one is the what do you call that one? Electron current, okay, or the counterclockwise. But in here, this is what I also use. Okay, well, to be exact, wherever is the positive polarity of the voltage source, that is where I always go for the flow of current. Okay, so I don't go the electron way. I always go with the uh, proton way or the positive way. Okay, so that is also the reason why we have this flow of current right here. Okay, so I think it's only logical because we have the positive right here. Okay, positive and the negative. The same with this one, we have the positive and then the negative. So that is why we have this kind of flow of current right here. Okay, so you don't need to stick, if there is a loop or if there is a mesh, you, you, you don't want to stick, with clockwise only. If it's counterclockwise only. So you can have both. Okay. So in here I've used conventional, but in here you've used, let's say, electron method. Okay. So you can go with that as long as in here you're call this when you're consistent, okay, with your signage or with your polarities. Like for example, in resistors, of course, this one will become a voltage drop, so positive, negative, and then another positive and then negative right here. Okay, and then in here the same. So we have positive and then negative, and then positive and then negative. All right. But anyway, so this circuit has three branches. So 1, 2, and then 3. Okay, and then two nodes, which is the A and B, and two independent loops. So this is one loop and then another loop right here. So using Kirchhoffs current law or KCL equations are given as, so at node A we have I1 plus I2 is equal to I3. Now, how did that happen? That is because we have this current right here going into this node A, and then we have another current right here, which is again going into this node A. So those two are already positive. So I1 plus I2. But we have a current right here, which is leaving this node A. That is why we have this equation right here, minus I3, okay, is equal to 0. And if you're going to transfer this I3 right here, you will come up with this kind of equation, I1 plus I2. All right, so that's how we've got this formula right here for the node A. Okay, and the same concept with the node B. So if we have another node right here, we're going to take a look at this one. So we have a current that is going in, which is the I3. And then we have node I1 and node I2, which is leaving the current. Well, to avoid confusion, you can just have one node for this uh, type of circuit. Okay, you don't need to have another equation in here. So you only need one, which is this node A right here, because they are just the same. Okay, this is the other way around. So we can use node A only, okay, which is this one. Okay, you're already good to go having this kind of equation. So you can say that this is now your equation number 1 from the KCL. Okay, and then you can just disregard this one, to make your solutions more simple. So after the KCL, you can now perform KVL. Okay, so of course, when it comes to KVL, you're going to solve for the voltage. Okay, so we have KVL1 or loop 1 and then KVL2 or loop 2. So let's start with loop 1 first. So loop 1 is given as positive 10. Okay, let's come up with another. All right, so let me just remove this one so we can come up with our own. Wala. Okay, anyway, I'll just copy and paste that one later on. So we can come up with our own equations. So our first equation from KCL, okay, at node A is we have I3 is equal I1 plus I2. All right. And at the same time, let me remove this one also. All right. And then for the KVL, okay, so we'll start with the loop 1 first. So KVL at loop 1, okay. So in here, in my case, I always start with the voltage source. And I always use the sign that is the one that is on the leaving side, okay, of that certain component. So in here, it leaves at the positive. So I will use positive 10 volts. Okay. But you can also go with negative 10 as long as, you know, you're consistent with your signage. But in my case, I always use the leaving signage of that component. So in here, we have positive 10 volts. And then in here, so we have another voltage. Okay. So remember that when a voltage source pass through a resistor, so of course it will perform voltage drop. Okay, so that is why we always have a negative sign in here, okay, at the outer part of this resistor. So because you know you can put here, okay, let me just clarify this one. I am the one who put those signage, okay, because you can put here negative and then positive, but this one is already incorrect. Why? Because it's like, you know, you're having another voltage source in here, wherein you will have this one added to your voltage source. So plus I1 times this R1 right here, I1 R1. Okay, so see, those two are already contradicting. Okay, because, you know, once it passed through this resistor, so it should perform a voltage drop because this is a resistor. So that is why we must have a negative signage in here. So to correct this one, this one should not be positive and then this one should not be negative. So this one should be positive and then negative because we always use the outer or the leaving part signage of this component. Okay. So going back to our solution. Okay. So in here we have negative I1 times R1. Okay. So remember the formula for the voltage, I mean the Ohm's law. So we have VIR. So this is a voltage. So this is still a voltage which is derived from the Ohm's law, which is the I times R. So if we have I1, we should also get the R1. Okay, so if we have the I total, then we should also get the R total. But in here, since we're dealing with individual currents and individual resistors, so we should use I1 and R1. All right, so let me just remove this one. And then in here, we have another resistor wherein, of course, again, it will perform another voltage drop. So negative, okay. So in here, we have I3, okay, this time. So I3 times R3, okay. So as soon as it goes back to our original voltage source, so that will be equated to 0. Okay, and then from here you can now, you know, put the equivalent values of those components of yours. Let's say R1, so it's already given, so just substitute the value of that one. So 10 minus I1, so R1 is 10, okay, minus I3, wherein R3 is 40 ohms. Okay, equal to 0. So this is now your second equation. Okay, equation number 2. This is your equation number 1. All right. So yeah, that's it for the KCL and then the KVL at loop 1. Now, we have another loop which is KVL at loop 2. Okay. So in here we have already put the signages. So we have positive 20 volts. And then we have here negative I2 times R2. And then we have another resistor in here, which is negative I3 times R3 is equal to 0. And then here we can substitute their corresponding given values, wherein R2 is 20, so that's times 20, minus I3 times 40 is equal to 0. Okay, so this is now your equation number 3. Okay, so we still have another KVL, which is KVL at loop 3. So this is your third KVL. So positive 10 volts, and then negative I1 times R1. And then we have here positive, okay, positive 20, or positive I2 rather. Positive I2 times R2. And then we have negative, okay, negative 20 volts. And going back here will be equal to 0. Okay, so 10 minus I1 times 10, and then I2 is equal to 20 minus 20 is equal to 0. So this is now our equation number 4. Oops.